Alright guys, it's time for the final and most exciting part of our course, and in this video we are going to be working with optimization. So you sort of had the basics for some of the really popular machine learning algorithms. Now it's time to take those algorithms to the max and really push the accuracy on how well we can predict cancer based on several different factors. So the first thing that we're going to do is we're going to connect to our runtime, and we're going to upload our cancer data set. And here's our breast cancer data set. And we're going to do some pre-processing. So we're going to say import pandas as PD. We're going to say data set equal to d.read_csv cancer.csv. And then we're going to set the x equal to, if you remember from the last video, dataset.iloc, and we're going to do colon, and then from 2 to 29 dot values, and the y is going to equal to dataset.iloc, and we're going to have 1 right there, dot values. Alright, so we'll run that. Next, what we're going to do is we're going to do our train test split, so that we'll have a test set to test how accurate our model is. So we'll say from Scikit-Learn dot model_selection, we are going to import the train test split, and we're going to say xtrain xtest ytrain ytest equal to train test split, our x, our y, and we'll set our test size equal to 0.2, so we'll have 20% of the data set aside for testing. Okay, so we'll run that. Looks like everything went smoothly. And now, if you remember at the very beginning, the pre-processing part of our course, we talked about scaling. So we're going to see if we can improve the accuracy of our model by scaling all of our values so that they're on the same spectrum. And in order to do that, it's really simple with Scikit-Learn. We're going to say from Scikit-Learn.preprocessing, we are going to import standard scalar, and then we're just going to say our scalar is equal to the standard scalar, and then we're going to say our xtrain is going to equal to scalar.fit transform our xtrain, and we're going to do the same thing for our xtest. So xtest is going to be equal to scalar.fit_transform xtest. So I'll run that, and now you can see that all of our values are scaled. So if I print out, let's say, xtrain, you can see here all the values are in a certain range. Okay, so now that we have that done, it's time to work with our first way of optimizing. And we are going to do something called principal component analysis. And in principal component analysis, if you noticed our cancer data set, we have a lot of different features of our model. Now, what principal component analysis is going to do is it's going to take those features and it's going to reduce them. So how does it reduce the features? Well, if you remember with linear regression, we had two variables, we had an x and a y, and we wanted to try to predict new variables based on the correlation between those two data points. And that's essentially what we're doing in principal component analysis. Now, given in principal component analysis, you are measuring the direct distance from the line, versus in linear regression, you are measuring the vertical distance away from the line. And what we're going to do is, if we have two variables that are highly correlated, what we can do is we can say, okay, so all of these two variables, the correlation is represented by a line, as you see here. Now, if it's represented by this line, we don't need to have the x and the y. We can just have the x as a scalar value, because we don't have to worry about direction anymore. And so that's basically how you can reduce dimensions. And it's super easy to implement, and you can get higher accuracy on your model if you have a lot of correlated features. And also, if your data set's really large, this can help reduce the dimensionality of your data set. So this is really useful. What we're going to do in here is we're going to take all of these features and we're going to reduce them to just 2 dimensions, and by doing that we can perform just simple logistic regression that we can actually print a graph out of. So we'll say from Scikit-Learn dot decomposition, we're going to import PCA for principal component analysis. And then we're going to say PCA is equal to PCA, and our number of components will just equal 1. So we'll take all of our x values and then just turn them into one single data point. So we'll say our x underscore train underscore scaled is going to equal to PCA dot fit transform x underscore train. And now, just to sort of show you what I mean, you see up here we have all these different values. If we print our x underscore train underscore scaled, and let's just print, let's say, the first 10 values, you can see right here that we've taken all these features and reduced them to just 2 features. Alright, so now that we have all of our x variables in one single feature, it's time to do some basic logistic regression. So first, let's just plot out our x and our y. So we'll just say import matplotlib.pyplot as plt. And we're going to say plt.scatter. And we're going to have the x train scaled and the y train. And then we'll run plt.show. Enter that, and you can see here we could easily perform logistic regression on this. You can clearly tell that there is a boundary here where it goes from 0 to 1. Now, obviously we have reduced the dimensions so much that this isn't going to be a very accurate model. For instance, this whole area right here is in congruence with this area down here, so we're going to get some inaccurate predictions. But we could make a very simple version of logistic regression using just 2 variables, just an x and a y, which I think is crazy. Okay, so now that we have that done, it's time to work with gradient boosting. And so far, the algorithms that we've used for machine learning are pretty vanilla. What gradient boosting does is, if we go back to ensemble learning that we learned about in the last video, it's going to make a bunch of different models, and then using something called gradient descent, which you'll learn about if you take my Keras course where we work with neural networks, it's going to use gradient descent to try to find the best model, and it's going to take different features from different tinier models and then combine them all together at the end to form one massive, very accurate model. And so for gradient boosting, we're just going to say from Scikit-Learn.ensemble, we're going to import our gradient boosting classifier. I remember you can also do this for regression, of course. And gradient boost, which is what we're going to call our model, is going to be equal to gradient boosting classifier. As always, you could adjust the hyperparameters if you wish. And we're going to say gradient boost.fit, and we're going to fit our x train to our y train. Okay, so let's run that. Next, what we're going to do is we are going to print out our confusion matrix and see how well our algorithm works on the test set. So we're going to say ypreds is equal to gradient boost.predict, and we're going to predict the x test. And then we're going to say from Scikit-Learn.metrics import confusion matrix, and then we're going to print the confusion matrix of the y test in comparison to the ypreds. So we'll print that out, and you can see we don't misclassify any here, and we get 6 classifications wrong here. So overall, that's a pretty good improvement of our model, and if we run this multiple times on multiple different test sets, we're going to get different values from this, but you can see pretty quickly we get a fairly accurate model. So now what we're going to try to do is we're going to try to do extreme gradient boosting. And extreme gradient boosting is pretty similar to regular gradient boosting, except extreme gradient boosting has a couple of hyperparameters adjusted, and as always, if you're interested in how that all works, people who are better at explaining it than me have done so below, and I've put them in the description for you to check out. But something that's really cool about XGBoost, or extreme gradient boosting, is that it wins more Kaggle competitions than any other algorithm. So this is an extremely powerful algorithm, and it's also extremely simple compared to some very complex neural networks that would usually win a Kaggle competition. And all you have to do to import XGBoost is just say imp from XGBoost, because it's a separate library which is already installed in Colab for us, luckily. We're going to import the XGB classifier. And then we're just going to say XGBoost is equal to XGB classifier. No hyperparameters for now. And we're going to say XGBoost.fit. And we're going to fit our X train to our Y train. Alright, so let's run that sucker. And now what we're going to do is we're going to do the same thing with the confusion matrix. So I'll copy that, paste it into here, and instead of gradient boost.predict, we will say xgboost.predict. So we'll run that, and you see this only makes 4 mistakes, whereas the other one made 6. So that's a pretty marginal, it seems like pretty marginal gain in improvement, but still, we have an extremely accurate model. And just like that, you guys have worked with gradient boosting, and you've worked with principal component analysis. You know how to make many different models. You know how to make those models more accurate. You know how to deal with the test set. You know how to make sure that your data set is correct for the problem that you've tried to solve. And you've really come a long way. So pat yourself on the back. And now it is time for our extra credit assignment. And in the extra credit assignment, I want to show you what a difference makes if we don't do standard scaling. So what I'm going to do is I'm going to run over the data set again, and we are not going to run this cell with the standard scaling. So if you see we run that, you see we have all sorts of different values, and we're going to see what happens if we don't scale the data set. So first, let's see what happens with principal component analysis. And you can see right here there is actually a little bit more overlap between the X and the Y than there was before, although not too bad. Now if we run gradient boosting, you can see we get actually a little bit more accurate for gradient boosting, and if we do extreme gradient boosting, we get an even more accurate prediction. So something that's important with transforming, with scaling your values, is that sometimes it doesn't work. It really depends on the problem. If you want to get a little more accuracy, it's worth a shot. But like as we've seen right here, sometimes it doesn't work because we have reduced our errors by half for the extreme gradient boosting and by 2/3 for the regular gradient boosting, just by getting rid of transforming and scaling the values. But yeah, guys, that's pretty much it for this video, and I hope to see you in the next one. Sweet. Congratulations. Thank you guys so much for making it to the end of this video. As always, if you enjoyed it, make sure to hit that like button. Also, if you have any questions, comments, or concerns about what we did in this video, please leave them down below. Now, if I could have just one more minute of your time, I would like to tell you about a service that I've been using for over a year now called Scribd. Now, just as a side note, Scribd did not sponsor me to make this video. I just wanted to tell you about it. Put simply, Scribd is a lot like Audible, except for instead of being $15 a month, it's only $9, and instead of only having 2 audiobooks per month, you get an unlimited access to a plethora of audiobooks, ebooks, documents, and even sheet music and magazines. So for me, this was obviously a no-brainer, and right now, if you use the link in the description, you get 60 days free of Scribd, and I get 1 month if you sign up using my link. So that's why Scribd didn't officially sponsor this video. I'm just telling you about it so that I can get some free months and I can continue learning, and you can also continue learning with your 60-day free trial. So thank you guys so much for making it to the end of this video, and I'll see you in the next one. Peace.